Okay, this is chapter 17, number 26 from the textbook, and it's a heavily conceptual question. One of the parts is particularly tricky, so I'll address that. The other ones are kind of more typical of what I think you would expect on an exam, let's say. So what we're looking at is this problem that involves making a solution from a solute and solvent and kind of predicting the relative sizes of the enthalpies for the steps and the overall enthalpy of solution, which just kind of as a refresher, the solution process, making a solution, is kind of broken down into 3 steps with their respective enthalpy values. The first 2 are going to be always positive, the third one's always negative. Won't really go into this. In my kind of first video from this chapter, I talk about this in more detail. You can check that out if you want. I'm sure it's in your lecture videos as well. And I just want to also point out there's a table in the textbook that kind of addresses problems like this, and it's figure 17.4, page 721, and I kind of summarized the important parts for this problem here, but I would definitely look at that, maybe write it down, that would be something that would be helpful in a lot of cases. So there's 3 types of solutions. This also really ties into Raoult's law with vapor pressure. So these deviations refer to vapor pressure. You have the ideal case, enthalpy is basically 0. Positive deviation, this kind of refers to having a higher than normal vapor pressure. So again, that's more of a problem or concept for a Raoult's law problem. And then negative deviation would be a lower vapor pressure. Okay, so this stuff does kind of far-reaching into lots of aspects of this chapter. So it's definitely good to get a handle on this. So we'll talk about just kind of the forces and how to tell kind of with the polarity of molecules. So what this on the right side here is saying, these are the IMFs, basically these little dots. So we have, the solute, let's say, is A, the solvent is B. And what you can also think about is this kind of column with A, the forces between A molecules is essentially the, what corresponds to the enthalpy stage 1. Solvent molecules, B, that would be delta H2. Delta H3 would be when you put them together. So what we're going to have is when we break apart the solute and the solvent particles, we're putting in energy. Those enthalpies will always be positive because we're breaking IMFs. And then when we form the solution, we're putting those solute and solvent particles together. That enthalpy will always be negative because we are forming IMFs, right? And so again, you're kind of like thinking about breaking IMFs here, breaking IMFs, and then forming IMFs in the third step, which is why that's negative. So in an ideal case, the overall enthalpy comes out to be 0. That's this first picture here, where the first 2 positive steps are exactly balanced by the third negative step, so that overall, the enthalpy of the solution is basically 0, right? Close to 0. In the second scenario with a positive deviation solution, you have the A forces and the B forces being broken, but the third step, the delta H3, those forces between A and B are relatively weak. That's what this inequality means. The forces between A and B are relatively weak, right? So what we get is that energy stage is going to give off less energy. So when we put in energy in the first 2 steps and the third step gives off energy, it's not giving off as much energy as it took to, break apart those solvent solute particles. So what we end up with is an overall positive enthalpy, or an overall endothermic reaction, which you could measure by, or just, I guess, see by mixing things together, and the temperature of the solution gets cold because that reaction is sucking up energy. In the third stage, it's the opposite, where the AB forces are relatively strong. So that third stage or step gives off more energy than you put in the first two steps. So when you get that, positive, positive, and then this negative step being relatively large means that now you're ending up below the enthalpy where you started. So the overall enthalpy of solution is negative or exothermic. This reaction, you can imagine mixing things together, that gives off heat. It's going to heat up the whole solution. The solution is going to get warm. So this, again, is also tied to temperature changes, which, again, is in that table in figure 17.4 in the book. It's got that temperature change as well. That's good to kind of link to this too, so you can remember how that plays into this. Okay, so anyways, that's a little background, but I think it's needed to really address this, especially the nuance with part B. So typically what we do is, I'm actually going to start with part C because it's the kind of easiest one. So you look at the polarity of the molecules because really with solubility and things dissolving, it's a kind of a polarity issue. So we have a hydrocarbon chain and another one. This one just has 7 carbons. This one has 6. So, but they're both nonpolar. So we have basically a nonpolar solute and a nonpolar solvent. Doesn't matter which one's which. So we get this scenario. Well, they both would have only LDF forces, right? Or I guess LD forces. LDF forces would be London dispersion forces. So these are the same. So this is where you get an ideal solution. Delta H, basically the solution being 0, because again, when you break the energy to break those individual substances apart is pretty much the same energy you get when you mix them together, same types of forces. So nonpolar would be what you can, mentally assign or write down to go with an ideal solution. If you have a nonpolar, like a hydrocarbon chain, or it's just anything that's nonpolar, and something that's polar, right, like water or anything else, then what you have, are this has dipole, also has hydrogen bonding because it's water, has OH bonds. So what you get here is that when you put them together, you're not going to recover those hydrogen bonding forces because water can't hydrogen bond to this thing. It just has carbons and hydrogens. So what you have is you end up, from water's perspective, putting in more energy than you really get out when you mix them together. So when you kind of take into account those relative forces, this ends up being a positive deviation. So you want to associate polar and nonpolar with positive deviation solution, delta H solution being positive, endothermic, getting cold, all that jazz, right? Okay. Now the ones that are a little bit trickier. A is just a good one to kind of keep in mind because this is one that I definitely have seen a bunch on tests and things like that, where you have two polar substances, and we have polar, but the first one, which is actually called acetone, that's the name of this molecule, has dipole, no hydrogen bonding by itself. Water, like we said before, dipole has also hydrogen bonding by itself. And when you put them together, you do get hydrogen bonding happening, right? Because the water molecule having the OH bonds can form a hydrogen bond to that oxygen from the acetone molecule. So you get this hydrogen bond happening here, right? Between solute and solvent. And again, because it's a relative thing, concept, that's what you want to keep in mind, is that if from the acetone perspective, you put some energy to break it apart, but when you put it with water, you're actually recovering more energy because you're getting extra forces that weren't present in just the acetone by itself. So this is I forgot to put a 3 here, the third scenario, the negative deviation, where you're getting in that third step of combining those two, extra energy coming out. These things really bond nicely, whatever analogy you want to come up with. They get, they like each other, right? They get along. So that third step gives off more energy than the first two combined. And usually the way we just kind of think about this, or the little rule we remember, is if you get hydrogen bonding between the solute and solvent, when one of those things didn't have it by itself, that's a typical negative deviation. So I'm just going to write that down and erase this part here. It's just drawing the hydrogen bonding, but let's say negative deviation. Delta H if solution is negative. Again, this would get warmer when you mix them too, because when you mix these two, because it's going to be kind of forming those extra strong IMFs, giving off energy when you form those stronger bonds. So yeah, H bonding and solute alone doesn't have it. Doesn't matter if it's a solute or solvent, but basically one of them, like the acetone, doesn't have hydrogen bonding by itself. It does with water. Okay, now for the weird one. Part B, you would kind of on first glance say, oh, polar, these things both have hydrogen bonding, dipole and hydrogen bonding. And oh, so they're like the same, and then when I put them together, I still get hydrogen bonding. Oh, by the way, how do you know something can hydrogen bond to water or to anything? You just basically need to have N, O, or F. So if a molecule has one of those, specifically with a lone pair, which they almost always do, then you can form a hydrogen bond to something with like OH. So basically all you need is the other molecule to have that. I should have mentioned that in talking about part A. Nonetheless, these two can hydrogen bond together, and they have them by themselves. So this would seem to be ideal. That's kind of what I think most people would predict. But it turns out, and this again is maybe only really discovered by actually measuring them when you mix them together and see what happens. But this turns out to be a positive deviation. Okay, that seems really weird because I think also if you're thinking about hydrogen bonding, you're like, well, it could be ideal. It could even be a negative deviation because they're forming hydrogen bonds when you mix them. But again, it's all a relative thing. So what's happening here, second scenario, right? We're not recovering as much energy when we mix them together as we put in. The reason is both of these things by themselves have hydrogen bonding, like we said. From water's perspective, it forms, pretty strong hydrogen bonds by itself. When you mix it with it, and this thing, by the way, is called ethanol, which is the alcohol that is in, beverages that we consume in booze. Ethanol does obviously mix well with water, but it's not, I guess, the same as just water and water mixed. You don't recover the same strength of hydrogen bonds because in this ethanol molecule, you actually have this CH3CH2 part, which is considered a nonpolar region, right? We're not calling the molecule nonpolar. It's polar, but it does have, 2/3 of it being kind of a nonpolar part. You can see with this colored energy, or this is actually a charge distribution, not energy. Like the red part's the more negative, the green, yellow part's kind of the more, not more positive or less electronegative part of the molecule, and that means that when you mix it with water can't really hydrogen bond to that side of the molecule, so it can only kind of stick to this side, right, and not to that side. So whereas other water molecules can stick all around it, ethanol, again, the forces that are being formed between the water and ethanol aren't going to be as strong as just the water and other water molecules. So again, makes sense when you think about on that level, but really hard to predict. And I think just a really tricky question. So in general, I usually tell people, don't worry too much about this. I mean, it is a book problem, so you should be aware if you see this one. but just don't worry about applying it to like every single possibility, because it is basically impossible. And you do have to oftentimes do the experiment and make the particular solution, mix A and B and see what happens. There aren't really good exact rules for like, if I mix this thing and this thing, what exactly is going to happen? These are all generalities, right? So anyways, hope that helps. Anyways, you can read in the solutions manual, it gives like a paragraph description of this as well. But hope that helps, and let me know by email or study hall if you have any other questions on this, and I'm happy to help you out. Okay, talk to you later.